Gettysburg Seminary presents the Seminary Explores podcast. Conversations on faith, art, people, politics, theology, life, and more, with voices from around the corner and around the globe.
Welcome to the Seminary Explorers podcast. This is Kristen Largent. I am your host today, and I'm very delighted to have as our guest my friend, Dr. Sharon Stephenson, who is in the physics department over at Gettysburg College. Sharon, welcome.
Thank you. It's a pleasure to be here.
It's great to have you. Those of you who have been listening to the podcast on a regular basis know that we have been interviewing some scientists from the college in light of the AAAS grant that we received to kind of integrate and think about the role science has in the seminary curriculum. So I thought it would be great to have Sharon to talk a little bit about what physics is and what physics tells us about the world and what people of faith, religious people in public ministry should know about physics. So Sharon, I thought it would be great if you could just start off by telling us a little bit about how you got interested in physics and your particular areas of research.
Well, first, how did I come to physics? As an American woman in physics, and I'm a full professor, I'm actually right now sitting in an endowed chair through the generosity of Gettysburg College. People like me are rare in this country, in that we're underrepresented in the field, women in physics. And so a lot of people ask me how I came to be where I am. And looking back, a lot of it has to do with my family. My mother she's retired now, but she was a chemist. My father, an engineer. My aunt, a biologist. My grandfather, a cattle farmer, which anyone who actually does farming, especially these days, knows that that's really a science.
Isn't that interesting, right?
Yes. Yeah. You have to have an enormous skill set and deep knowledge of all kinds of things to run a successful farm, large scale. Anyway, that's where I came from. And then in high school, I had no intention of majoring in physics because my older brother was a physics major, and heaven forbid I do, right? Heaven forbid I do anything related to something he was pursuing. But I was also fascinated by certain things with sort of morbid curiosity, especially for Chernobyl. Chernobyl occurred in April 1986 when I was a high school senior.
Yeah.
And so that's one of the little political threads that kind of wove its way through my life. And my senior year of college, I went to a small liberal arts Methodist college, Millsaps in Jackson, Mississippi. And there I had the great fortune to go do some research somewhere else at Florida State University. And they just placed me with a bunch of nuclear physicists. And I loved them. I loved the teamwork. I loved the camaraderie. I loved the challenge. And it kind of scratched this itch of understanding nuclear physics because, like I said, I had this almost spooky fear of it, as most of us do, right?
Yeah, sure.
It's invisible and all of these things. And there's Hiroshima and Nagasaki and all of these things. So I went to graduate school in nuclear physics because what else would one do?
Were you the only woman in your program?
In undergraduate, yes, but in graduate school, no.
Oh, good.
And then from there on, I've continued to widen the circle, and it's been really great. So I am, in full disclosure, a nuclear physicist. What I study is called nuclear structure. So I look at the way neutrons and protons actually pack within a nucleus. And you would think we understand that because we can harness nuclear energy in the form of power. We can build weapons of mass destruction. We can treat cancer. All of these things using nuclear physics. And yet, we don't know. I can't write down for you the beautiful mathematics that would describe the nuclear force in the same way that I can describe the way charges interact with each other, the beginnings of chemistry.
I want to ask you just quickly, when you say nuclear physics, you mentioned, so Hiroshima and Nagasaki we think about, but then I was thinking like nuclear, like nucleus.
Yes.
Is it the same? I mean, how these things seem like one seems really small and tiny over here, and then the other thing seems really enormous. So how are they related? How does this looking at electrons and protons relate to the atom bomb?
Okay. So the nucleus, nuclei in general, are, of course, I think they're beautiful. And
of course you do, weirdo.
and they're very interesting because you have something like uranium or plutonium, which are the things that we make weapons out of. And the reason that we can make weapons out of them is because their nuclei are so big that they have a tendency to want to easily fall apart. And so if you add a little bit of energy to the system, they will do what's called fission. So you've heard of fission bombs, fission weapons. And so they do fall apart, and in doing so give out enormous amounts of energy in the form of radiation and heat, and you have a bomb.
Okay.
And when I was a graduate student, I actually studied those larger nuclei because they're absolutely fascinating in many, many ways still, and to nuclear physics. I mean, you would think, we've done it all, but we haven't done it. We've only scratched the surface.
Yeah.
I know that we were able to get all of this power, either destructive power or healing power, in the form of the way we, like I said, approach cancer treatments. And yet, there's just a lot we don't know. We just base it on experimental results we have from the past, but we don't know the girding. We don't know the scaffolding. We don't know how nuclei actually, how the individual nucleons within uranium or plutonium or even oxygen, how they really talk to each other.
Yeah, that's amazing.
Yes, because when you think about it, you look at the periodic chart and you ask why. Why is it only that size? Why not 3 times as big or half the size? And that's basically chemistry, because those still have we're talking about the electrons.
Okay.
In terms of the way neon is a gas that is noble. I love the word noble because of its electron structure. But I don't care about electrons. I mean, they're nice, but they're too small for me. I like the nucleus, and so the nucleus of neon, for example, is interesting in its own right, but we don't look at it in terms of the periodic chart. We have this other chart called the chart of the nuclides that has hundreds and hundreds and hundreds. I know. But it's big, it's huge. It has hundreds and hundreds and hundreds of things on it because it lists all the isotopes of neon and all the isotopes of calcium. But calcium has a number of stable isotopes. In other words, isotopes that are radioactively inert. They don't do anything. They don't decay. You can drink them in your milk.
Yeah,
you can have them in your bone.
Okay, yeah.
And you're happy, right?
Okay.
You can have them, and there's lots of stable isotopes of calcium. Why? Why so many? Why not 1? Why not 3? Why so many? And these are the questions that nuclear structure physics, physics, is trying to figure out.
Okay. So explain, another thing that you had mentioned that I'd love to hear in terms of thinking about kind of some of the practical ramifications. You've mentioned a couple times now in the way we treat cancer. Mm-hmm. How does what you do relate to cancer research?
I'll give you some examples. So when we use radioactive materials in 2 ways with cancer: in diagnosis, in trying to find hotspots of cancer in the body, and then in treatment. So, for example, in hotspots, cancer cells divide quickly. And so you can capitalize on that and do something like give a patient sugars that have some radioactive isotopes in them that are short-lived. Because, yes, does this hurt the patient? A little bit, but not as much as cancer hurts the patient.
Yeah.
And it's short-lived, it's minutes long. And you can then image the body. You can look at the, usually in this case, the gamma radiation coming off of the body, and it leaves a signature of where the cancer is.
Oh, wow.
Yeah, because these active places where the sugar's being taken into the body in these hot spots, that's where cells are multiplying fast. Well, what multiplies fast? Cancer cells multiply fast.
Okay.
And then if you want to kill cancer, or kill cancer cells, then there's all sorts of really interesting technologies how you can put radioactive material that lives relatively for a short amount of time into tumors, and you can then basically destroy them from within instead of having to go into a person surgically and remove. So it's commonly used. There's little pellets that are being used. There's some wonderful research right now using what's called, maybe you've heard of graphene. Some people won the Nobel Prize. Now it's probably been close to 10 years ago for discovering how carbon can be made into really smooth sheets. And they even use Scotch tape. They're, I think, the only Nobel winners. Yes, I think we're the only Nobel winners that took
kind of MacGyver to...
Yes, totally. Kind of MacGyver. But we're looking at, we being nuclear physicists, are looking at ways to take these graphene tubes and pack them full of radioactive material to allow that, because the graphene itself, a cell doesn't reject it, and it can go right through a cell membrane into the heart of the cell, and then deposit that radiative material effectively to destroy the cancer cell in this sort of targeted way. And also, you've heard of people who they go to get radiation treatment. Right. Yeah, and so we have all different forms of radiation treatment, and we are investigating how you can use different isotopes. I love the word isotope, to help image the body better. Like there's some isotopes of xenon, for example, that you can do something called polarizing, almost like polarizing your sunglasses. But you can polarize the gas so that when people breathe it in for lung imaging is really hard because there's just not a lot of stuff to image. It's just basically an empty thin bag of skin that you're trying to image. And so if you can get a brighter image with this polarized xenon, for example, then you get much more information from the patient.
That's amazing.
Yes, and so it's this wonderful marriage between medicine and what we all consider a radiation. But on the other hand, it also has, of course, its dark and wicked side, which is the weapon side of it, which is dark and wicked.
Well, tell me, you're a nuclear physicist. Tell me about the other kind of physicists that are in your department and some of the different things that they do. And what's the overarching, what makes somebody a physicist? Like, so the last conversation that I had was with your colleague, Dr. Principato, who's a geologist, and she said, rocks, and it's more than that, of course, but like, what do physicists study? I mean, what makes you a physicist, not a chemist? You mentioned chemistry.
Yes, and I would like to say that I think 20 years ago the answer would have been cleaner. Than it is now, because 20 years ago I would have said we're fundamentalists. I mean, we study the fundamental properties behind chemistry, behind biology, behind geology, all of it. We are the ones kind of one step further back in terms of theory. I don't know if that's true anymore. Physics has become breathtakingly interdisciplinary, and it's kind of been, I almost say, explosive in how it's grown in the last few decades. And I'll give you an example by just telling you what the people in my department do, and then you'll see that it's just not a one-stop shop anymore. And then I'll circle back and try to say what physicists really do now, because it's a strange thing. So I'm a nuclear structure physicist. And so I need equipment. I need a lot of money and a lot of equipment to do the work that I do, and lots of people, huge teams of people. We have another nuclear physicist in the department. Also, his work is completely different. He studies neutron interactions just with bare neutrons, where I'm studying clusters of neutrons and protons together. Then we have a plasma physicist. Yes, plasma, which is plasma is its own state of matter, like liquid, solid, gas, and then plasma. So it's like a charged gas, if you will. So he studies things that have direct applications to solar weather, because corona discharges from the sun, and space weather and all these things are dictated by charge up in the upper atmosphere. So he has his own plasma device. And here's, for the Gettysburg people, it's called the Pickett's Charge Device. Yes.
Of course it is.
Of course it is. Because we're in Gettysburg.
Funny.
And it's fabulous. And that was built by students. And he also does nonlinear optics, because he uses lasers and optical techniques to study these properties of plasmas, because optically you can't see much at all. It's a diffuse gas that charges, right?
Yep.
So, and that's the work he does. He has... and all of us have work that we do on campus with students, and then almost all of us, I think every single one of us also has work that we do off campus with students too. And then we have an astronomer who studies spotted stars. You've heard our sun has sunspots.
Yes.
Well, our sun is not unique in that. So there are lots of stars. In fact, most stars have sunspots. And so studying the sunspots, even of distant stars, we have the capability, which to me is just mind-blowing. We have the capability to study sunspot cycles on other stars. And in doing so, we can then understand how these stars actually evolve and how they're...
So sunspots aren't permanent?
No, sunspots move around on the sun's surface. It's a very dynamic, like 12 to 14-year cycle that these things go through.
Oh, okay.
Yeah.
And can tell you something about the lifespan of the... Or
we actually are pretty good at telling you about the lifespan, but it can tell us about what's happening inside the star in terms of sunspots are created by magnetic fields that are coming in and out of the star kind of dynamically. And so as these things move across, because the sun and all stars are not at all solid. And so it tells us about what's happening, the dynamics of what's happening within the star and how fast the internal part's rotating relative to the outside part. Really, I know.
Yeah.
All of this information you can tease from light.
Do you have the equipment at Gettysburg College, or does your colleague do that work a place where there's a telescope? Is that what you need? A bigger telescope, some enormous?
She applies for time and gets time on a telescope out in Arizona, in Flagstaff, Arizona. But we also have our on-campus telescope. We also get good data from that telescope as well. The Gettysburg College Observatory, for example, has found, I think, at least 3, maybe 5 new asteroids.
Really?
Yes.
Isn't that great?
And one of them is named after the daughter of one of our astronomers. Because you get to name it.
There's no Pickett's Charge asteroid.
No.
Feels like that'd be a bit too far, right?
But one of them I do believe is named Gettysburg. There's one asteroid.
That's so great. Isn't that funny?
It's fabulous.
Yeah.
So, and then I'm trying to go in chronological order here. That's why I'm pausing and going a middle list.
Yes.
Then we have the next in the list is a biophysicist. So here's another bit of, I know, exactly. Yeah. So you would think, well, how do biology and physics marry? And here's one example. This is why I said 20 years ago, what would you have called this person?
Okay.
DNA packs into a cell. There's just so much DNA that we're not sure how it actually folds up into a cell, because in terms of its charges, it should be really repulsive. And so how DNA packs in cells, we don't know.
Okay.
And that's basically his research area, studying that.
Wow.
And why it can even be interesting, beyond just the fundamental question of how and why, is one thing we'd like to do is figure out how stem cells do what they do.
Okay. And just say again what a stem cell is.
A stem cell is a particular kind of cell that can regenerate itself. It has its DNA keeps certain receptors kind of live, so that, for example, in a lizard that loses its tail, it regrows its tail. Mm-hmm. And we don't have, we have stem cells when we're still in the womb, because we're developing all these different kinds of, we need to grow our arm and our eye and our hair, and the stem cells do all that, but then once we're born, we don't generate any more stem cells. And so, of course, the medical profession would love to figure out how we could turn our DNA on in such a way as to say, hey, would you mind acting like a stem cell so that this person who's lost their eye could regrow another eye that's just like the one they had.
Right.
And that would be, because that's what fish do. Fish get blinded there's many kinds of fish that lose an eye and they can just regrow their eye.
Yeah.
And they're much simpler animals than we are.
Yeah.
And yet they can still do it and we can't. So that those again, and that's physics. It's an interesting,
really,
yeah. I mean,
okay,
because when you think about it, it's besides the DNA part, which is clearly biology, but you're thinking about the charges on the DNA, the structure, the fundamental way it interacts. So telescoping out for a minute and thinking about what physicists do, we are interaction fanatics.
Okay,
and I bet I'm the only person who will ever call a physicist an interaction fanatic. So that's really what we are, all of us in our department and every physicist coast to coast, we are fundamentally interested in the way things interact with each other.
Yeah.
So the next example is another astronomer, Ryan Johnson, who studies the way galaxies merge. So believe it or not, galaxies often do whack into each other. I mean, they don't whack, but they slowly merge into each other. And he does beautiful work in terms of the computational pictures that this man makes are fabulous. in studying the dynamics of how galaxies come together, and we can learn a lot about that from that process. The next person in terms of interactions would be James Puckett from North Carolina originally. He's one of our Southerners. He's about 7 feet tall. No, he's not 7 feet tall, but he seems like it to me. Very tall guy. He studies soft condensed matter, which you're like, what is that?
I know. I thought you were going to describe a food. Soft,
yeah, it sounds like Jell-O.
Right.
No, and so he studies using the laws of physics. He studies swarms of midges. And right now he has got some tanks in his lab where he is getting fish, and he is looking at how flocks of birds, people in Tokyo crossing the street, large scale, how physics can predict or understand group behavior when there's lots of variables.
Oh, that's interesting.
It's very interesting. Very, very interesting. And again, it's interactions.
Yeah.
But you can say, wait a minute, a physicist studying a school of fish, who cares? But the fact that you can take these fish and then say, I'm going to pretend like they're a gas of particles and that they don't even know each other. Yeah. And look at how that, and then I'm going to keep adding levels of complexity.
Well,
it's amazing.
One of the thing that I just thought of when you were talking about the one of the things, even though I know less than the smallest bit about physics, I remember reading about kind of the shift from Newtonian mechanics to, and so one of the things, so again, reading about it, particularly as it relates to theology and religion, right? Mm-hmm. I mean, a lot of there have been interesting comparisons done about Buddhism in particular in physics, because Buddhism, I think we come often in the West, we come out of this kind of Enlightenment model of these kind of individuals first that then have relationships.
Yes.
And Buddhism is the opposite. It talks about first, there are all these relationships out of which individual things come, or things that look like, And I feel like one of the things that I think is so fascinating about physics is when you get down to it, it's all relational. And the whole thing about, is something a wave or a particle, right?
Yes.
That was actually, it depends on how you measure it. It's kind of both at the same time. And this to me is a really revolutionary idea about creation itself. And so it's not that we're these discrete parts over here and there, but actually there's this network of deep interrelationship underlying it all. That's just amazing to me.
It absolutely is. I mean, people, for the most part, most physicists tend to be to not be, and this is, and I might be wrong. I don't have statistics on this, but in my history, most physicists tend not to be very literal in terms of scripture.
Okay.
For example, so
sure.
we lean way against fundamentalism in any form. But I think all of us seek the beauty and mystery of the unknown, which I think all of us do.
Yeah,
but
right.
We're doing it from a different,
right.
A different lens, or looking at things through a different lens than perhaps a theologian would in a particular construct. But physics, what you said about Buddhism versus Western religions, physics often talks about, now it's just part of the lexicon, fields. We're all in a field, and I don't mean like a field of grass, but
that too, but
yeah, that too. A gravitational field, or an interaction field where particles can interact with each other, and then you ask the question, over what distance, and then what happens when you do a measurement? How does the observer?
Right.
Yes. And this is all the spooky stuff. So, I mean, for someone who says you don't, Kristen's sitting here saying, I don't know anything about physics, but then you bring up particle wave duality. This is a pretty sophisticated, very difficult concept to wrap your head around, which is one reason why it took us so long to accept it. Chaos theory, for example, which came up in the 80s, it was very difficult for us to I think originally accept that all these things that we thought were noise, that's a noisy electronic signal, or look at that over there, that's just noise in the data. could, in certain situations, actually be, it's structure. It's structure within what looks like disorder. And then chaos theory was born, and it does very well. So there is this inherent complexity and beauty in physics that I don't think, and of course this is why I'm a physicist, I don't think any other discipline can touch. I mean, biology, for me, for example, has a much more a direct human consequence. I mean, you find an Ebola vaccine, and it's clear that you have made a mark in this world. But and I'm not saying people shouldn't be doing that.
No, well.
But
pro Ebola vaccine, just to be clear.
Ebola vaccine. But I think physics, sometimes people say, well, as a physicist, what good? Where's the good? Where's the better good? And it is, in my mind, more akin to music and art than it is to, in many cases, than to finding a better vaccine. Because the work that we do is, like I said, very fundamental and seeking sort of these bare truths. Mm-hmm. Well, why does the Ebola vaccine work? Yeah. Okay, you've shown that it works, but I want to find out the mechanism why, so that then I can do that same mechanism to every other kind of disease that we have, on this planet, that kind of thing.
Yeah, which explains why it pairs well with so many, like why you said you were so, deeply interdisciplinary, because so much of what you do then, is in these great conversations with other disciplines.
And that's the way it is today. I mean, I cannot think of a pure physics. Cosmology might be one, the only one maybe left. And all the rest of them have there's no astrophysics anymore. Name your discipline. There's nuclear astrophysics. There's computational astrophysics.
Okay, I see.
I mean, it's where we all have multiple labels now.
Yeah.
I can't even say I'm a nuclear physicist anymore. You heard me say nuclear structure.
Yeah.
That separates me from someone. We're all very. I want to say more precise in the way we talk about ourselves, but we also really understand that the work that we do has lots of applications.
Yeah, that's great. Well, this is Kristen Largen with Seminary Explorers Podcast, talking with Sharon Stephenson, a full professor of physics down at Gettysburg College. We've been having a great conversation about physics in general and some of the different specialties and ramifications. But Sharon, I'd like to take some time also to, there were a couple things that you mentioned, a couple things that I'm thinking about in terms of sort of things that are going on today, and again, some kind of practical ramifications. And so I wanted to ask you about the God particle, right? Because look, there's God in an article about physics, and so it's the hadron something.
The Higgs boson.
Yes, Higgs boson particle, but isn't that at the collider?
At the Large Hadron Collider.
Yes. See, I'm just almost. So I want to hear about all that. I want to know what it is and why it is called the God particle.
All right. Well, I'm going to disappoint you.
Oh,
in that
is it not the God particle?
No, I mean, there is no such thing as God.
I know. I want to know why it was called that. Maybe it was just a news reporter who thought this is going to be a catchy headline.
I think you're more in the right ballpark.
Okay.
And that it's been this particle that we have.
And remind me what it's called. Say it again. What it's called?
The Higgs boson.
Higgs boson particle.
And it's called the Higgs boson because it's a theoretician whose last name is Higgs was the first person to suggest that this type of particle with these kind of characteristics would kind of complete this theory that many of us currently accept called the Standard Model.
Okay.
And I do have to step back and say the Standard Model doesn't explain everything. Okay. It only explains some things. For example, I said, nuclear physics, we don't know. I can't write down the formula. There's still so many stones that we have to turn over in this great universe. And we don't understand dark matter. We don't understand... you
guys have really cool names for things.
I know,
dark
we
matter.
do. Dark
Love
matter. and then there's so many big questions that are sitting out there. What is the structure of nuclear physics, for example? Why does the chart of the nuclides in the periodic chart look the way it does?
Okay.
Tell me. So anyway, the Higgs boson is the standard model is a more fundamental model that actually helps us figure out why we have the particles that we do, like protons and neutrons and electrons, and why they act the way they do. Why and why don't we have more particles or less? And so some people nickname it the particle zoo, that there's all these different kinds. And the Higgs boson is this sort of very fundamental particle that we believed existed, but to actually experimentally determine that it exists, we needed to do collisions at very, very high energies. And we couldn't do that until we built the Large Hadron Collider. The God particle, though, is the most unfortunate name one can come up with. And I really do think it was, and this again is just total, my poor memory. I think it was a publicist.
Okay.
For the book called The God Particle, written about the search for the boson.
Okay.
Or maybe a long essay that was in.
Yeah, trust me, the God particle is going to sell more books than the Higgs boson particle.
Doing a search for the Higgs boson.
Yeah.
And I was like, what's that? And what I love about that entire journey, and there is a wonderful documentary called something. God, worst podcast ever.
I know.
Called something with the particle. It has the word particle in it. But you can probably, if you did a Google search on Higgs boson particle and then documentary, pop
sure,
right up.
Of course.
And that I really like that documentary in that it really shows how it's a team effort, and it also shows how careful we are, because there were many experimental groups that came together and said, here are our results, and here are these other results, and here are these results. We didn't talk to each other about them. We were hopeful. Here's how well and how poorly our equipment can detect these things, because that's really what limits us.
Sure,
is the equipment.
Yeah, it's amazing.
And that's what moves us forward, to the equipment.
Right. And
so when these people come together, the honesty and the humility and the hours and years and of hard work that they put into it is it's humbling.
Yeah.
I mean, it's really, really something.
Yeah.
Because we've had parts in our history where we've jumped the gun and said, oh, we've seen so-and-so, and then had to backpedal and say, whoops,
nope,
actually we didn't.
It?
And there's lessons to be learned from that. But it's such physics now, especially now, I think, as the questions get harder, and as we push up against the technology more and more, it relies on teams. It's no longer, and in fact, people even say, "Oh, Einstein." One dreams of Einstein sitting alone. He was, of course, he was interacting with other people. Every physicist that I know, maybe thinks deeply alone at times.
Yeah, sure, but
then has to have the human interaction. For accountability's sake.
Yeah. Okay, so I want to ask you about the Big Bang Theory.
Yes.
Not the show, even though that again, we could talk a lot about the show. But is that still that's a discovery of physicists?
Yes,
I assume. And is that by consensus still the model that people think about? And what is it exactly? I mean, I think one of the great things about talking with you all in the fields is it pushes us, because general things that have entered the lexicon in a very generalized kind of way, but I think if people are pushed to really say, well, what actually does the Big Bang Theory describe, and how, again, is it controversial, uncontroversial? So I want to hear a little bit about that, maybe.
All right, so I would say 99.999. I don't know any physicist who doesn't believe. And I shouldn't say believe, that's even the wrong word, who doesn't support all of the experimental evidence.
Okay, yeah, right, that's right.
That points to a localized event that happened about 14 billion years ago that gave rise to our universe.
Okay.
Now, what actually happened in the very first few fractions of a second, we're still parsing that out.
Okay.
But we're pretty good. Like even I was even a second into it on.
We're there.
We got that. We got back on that. But and so the Big Bang theory says that, and then, but I do have to say this. If you say, well, what caused it?
Okay.
I think 99.9999% of us would step back and say, that's outside of our purview.
Okay.
Like that's the question for theologians and for
we have some answers for that.
Yeah. Right. But why then? What was it?
Okay.
Was there another universe before ours? It's extremely likely that there was. It's extremely likely that there. Well, if you believe the most of the current data that shows the universe is expanding, it means that eventually it will collapse. Yeah, it can collapse back, or some people believe that it's going to expand and expand and expand and expand, and then we have this what's called cold
dark death.
Yes. And again, that data,
hot death or cold death. I mean, is that kind of the okay?
That data. I particularly, to be honest, as a nuclear person, I'm not worried about. I'm more worried about Fukushima.
Okay, right, yeah, okay.
Like small scale.
Right.
My time frames are different.
Yeah, right.
But, we get new information in. In fact, I think it was just last week that one of the astronomers that lives here in Adams County, who you might want to talk to, Craig Foltz, fabulous astronomer, he was just telling me that a new galaxy was seen that's 13.5 billion years old. Well, the universe is 14 billion.
Wow.
So how did a galaxy get its act together in half a billion years? I mean, it doesn't make sense because the stars need time to coalesce and to get hot and to live and die and go through this whole process and yet there it is. And the data the astronomers are pretty good about figuring out how old a galaxy is. And so is there a problem in our measurements? Maybe things that are really far away, which this one is, and really old, maybe the way we calculate their age is a bit wrong. Wow. And maybe it really isn't that old. Or maybe it is, and then we've got a whole bunch of new physics to think about, because how did that happen?
So quickly, relatively speaking, right?
Yeah. But back to Big Bang. I mean, Big Bang, we have all kinds of evidence, and I think the most compelling evidence is what's called the 3 millikelvin background, which is just a cold background. But what it does is, if you say, okay, if there was a Big Bang and the universe expanded in this particular, and I wouldn't even say expanded, but that's the only word I've got right now. But the universe grew in a particular way, at a particular rate. Then when would what then would cold space look like? And the results basically say, well, how cold would it be? And 3 millikelvin is how cold it would be. And so you look at this and you're like, oh, well, maybe we're wrong. So we study it again, and we're like, it's still 3 millikelvin. I mean, we've studied it and studied it and studied it and measured it different ways, different times, different. And so I have no doubt, believe it or not, in the idea of a Big Bang. But I still will go back, because I know this is going to be heard by many seminarians, to say that we all beg off about what happened before and why. I mean, do I believe that there was science before? Yes, but I personally also believe that the science itself is so beautiful and magnificent that why can't it be the way some of us envision what other people call God? Yeah. Why can't a knowledge base be
right?
Divine.
Right, yeah. Right. Isn't that interesting? And just, I don't know if you can even explain this, but for people who would want to know, what are the kind of measurements, what is the kind of data that you're saying everybody looks at and agrees, yes, this points clearly to the Big Bang Theory. So people would say, and again, I think this. So if I wanted to say to somebody, if somebody said to me, oh, there are lots of theories out there. The Big Bang is just one of many possibilities for thinking about how the universe came into being. So is it the distance between stars? Is it that you kind of mentioned
that
the expansion?
Yes.
I mean, what kind of specific data points, does that make sense? Do physicists point to say this is why we think it was this and not anything else that it could have been?
Yeah, so this background radiation is one of them. This cold background, and that's the big one.
Okay.
But the other thing is the what's called the I'm going to say homogeneity, but space is completely isotropic. So I'm trying to think of the noun that is isotropy. Isotropy. There it is. Isotropy.
Yeah, right.
Isotropy of space and the homogeneity of space. In other words, if you point your telescope in any direction, then there's a uniformity to the universe. That again, how flipping the question around, how else would you explain? So people come up and they say, people may come to you especially and say, oh, well, besides the Big Bang, there's all these other theories. And I get emails in my inbox all the time saying, I've got a new nuclear theory, blah, blah, blah. And the immediate response to something like that for all scientists is, okay, you've got a theory. What experiment do you propose that would test this theory?
I see.
And that's what a lot of and I'll go ahead and be controversial here a little bit. Creationism and some of these other pseudosciences don't have any predictive power. They can't say, well, if the Earth is only 5,000 years old, then we should see this, this, and this in geology, or this, this, and this in astronomy.
Sure.
They can't say that because, well, right now all the data points to a much older Earth, a much older universe, and things like that. And the uniformity of space, the signature of deep, deep space, all points to the fact that 20 billion years ago we weren't here. I mean, but then again, we have no way of testing what might have been before us.
Yeah, right.
And we may never.
When
you think about how we would be able to test that right now, we don't have a way. So that's why we beg off. We're like, well, if I don't have a way to test it, And I'll give you an example: string theory. Yeah, there's been string. Everyone's heard of string theory.
And again, I've heard of it, but I don't know what it is.
It's a way that describes fundamental interactions, where we really care about the way things interact, at a very, very small level. So, gravity, which and quantum mechanics, which we've all heard of, disagree at small scales and at really big scales.
Okay.
And so, string theory is one of the theories that came up with. It's mathematically gorgeous. Oh my goodness, it is just something else.
If you can say that about me.
It is beautiful.
Yes. Okay.
And so lots and lots of string theorists have built their careers on how elegant and sophisticated it is in describing in reconciling these problems that we have right now with gravity and quantum mechanics being two separate theories that don't mix, for example. But then how do you someone like me says, well, how do you test string theory?
Right.
Give me an experiment to do.
Yeah.
And 15 years ago people would say, we don't have one because we don't have the equipment that could and so then my eyes get really squinty, right? I don't like that. And so the Large Hadron Collider, I'm hoping in the next, maybe it'll be 5 years, maybe it'll be 7 years. Optimistically, it could even be just a few years from now. When it goes through its upgrade, we'll have the capability to finally do some experiments that will touch a little bit on the on some of the experimental results will lift up or refute certain fundamental aspects of string theory. But look how long it's taken, and we have this theory, we have this theory, we have this theory. So I'm saying even within physics, we have theories that we have no way of testing at that point. And we're all skeptical, right? Just like with creationism or other isms or other theories that say here's how the universe came to be. You can have the theory, but none of us are going to say woohoo until you've got some experimental evidence that can back it.
Yeah.
Has predictive power. It has to have the power to predict.
Power. Oh, that's very interesting. Well, one of the things, and then we could keep talking, but I think that's really helpful for me. So we're always here at the seminary. We're really trying to explain why science and religion aren't enemies, why they're not diametrically opposed, and how actually they can be in really good, rich, helpful conversation, and especially for those of us in public ministry, how we can be informed, in really positive ways by the work of science. And one of the things that you pointed out is there's a theory that's sometimes called like the God of the gaps. And so anytime we don't know something, well, we plug God in there. But of course that's so silly because, like you said, we don't know this now, but 5 years, 10 years, 15 years, we will. And so, we've got to take God out of that and put God in somewhere else. And that's such a silly way to think about God, I think, right? And so what I hear in the work that you're doing is a challenge to really think about, well, how does what the Christianity teaches and the way that we talk about God, how is that, again, influenced by the sort of work that you're doing and encourages, pushes us, challenges us, right, to think in sort of new creative ways, like this idea about God as this sort of giant data knowledge system. I mean, what would that mean? What would we gain? And when we think about that, what would we lose? I mean, for a lot of people, of course, we want a personal God, and so, right. But how might that model or that image, right, help and shape the way we think about God? So it's really. So thank you for coming and talking to us. And because I just think that the more that people who are in public ministry know about science, the better work they can do in their congregations and just in the world to kind of help this idea to not think that science is evil, science is wrong, science is says religion is wrong. I don't think it has to say any of that.
Oh, no,
so
absolutely not.
Alrighty.
Yes.
Thanks so much, Sharon. It was great to have you with us.
Thanks for having me.
You have been listening to The Seminary Explores from historic Seminary Ridge in Gettysburg, Pennsylvania, a production of Gettysburg Seminary. We invite you to visit our website at www.ltsg.edu. Opinions expressed on this program are not necessarily those of Gettysburg Seminary or the Evangelical Lutheran Church in America.